Um, so thanks a lot, first of all, to the organizers for inviting me and giving me the chance to lecture. It's a huge honor to be able to talk at this school. So I'm really pleased, and thanks to all of you for sticking around. I know it's week 4, it's the last lecture of the afternoon. Everyone is tired, and there's a whole week to go. So thanks for sticking with it, and I hope you'll get something out of this course. So we have 4 lectures in which to learn all of string theory and all of mathematics. So that's what we're going to do. No, of course not. But since it is the last week and I know people are a little bit tired, my plan for the first 2 lectures, which will hopefully be easy on at least some of you, is to really review some very basic facts about worldsheet string theory. So for those of you that have taken kind of an introductory string theory course somewhere at some point in your graduate studies, everything for the first 2 lectures will be completely familiar. There'll be nothing particularly new. And if you're in that position, you can feel free to take a nap. And rejoin by lecture 3, where I'm hoping to introduce some new things that will have more close connections to mathematics. And if you haven't really had a chance to encounter any worldsheet string theory before, then I want to use the first 2 lectures to introduce the subject a little bit. Obviously, I can't be completely pedagogical, but to try to get us all on the same page and introduce some basic string dualities from the point of view of the worldsheet before we get into the more mathematical content in lectures 3 and 4. And so my goal in these lectures is to really, by the end of lecture 4, get you guys comfortable with the basic techniques and tools and even some terminology that you'll hear used in the more mathematical part of the field. From my point of view, there's a huge richness and diversity of interesting stuff going on, even in just the mathematical physics corner of string theory. But understanding where these things come from boils down to really understanding a few basic ideas that I'm going to try to get across to you. Things like cohomology, localization, and algebraic structures, algebras of operators. So that's really going to be the essential content of lectures 3 and 4. So today we'll just start with the Nambu-Goto action, and by the end of lecture 4, you'll know what an A-infinity algebra is, and you won't be scared of it, at least timing permitting. So, and I'll also try to be available and attentive to the Slack channel, GatherTown, that sort of thing. Since I can't be completely exhaustive in these lectures, I'm going to have to be quick through certain parts of the presentation, but feel free to ask me in GatherTown, offline, however you prefer to do that. Okay, so nothing else on this page. Okay, so let's get started. So as I said, what I want to do in this lecture series is just to provide an overview of some basic dualities in string theory, particularly dualities that are taking place on interesting space-time manifolds. So if you've never heard of if you've heard of but don't really know what Calabi-Yaos are, you'll get to meet them in this lecture. And I want to introduce some of the techniques that we use to test and explore these dualities when we have some supersymmetry in the game. And in those contexts, we can make particularly close connections to mathematics, although I really want to stress from the outset that neither the existence of dualities nor the existence of interesting and beautiful connections to mathematics depend on having supersymmetry, but we know a lot when we have it, and that's kind of a crutch that we're going to use today, and we'll still get a lot of great things. So just as you saw earlier in the lectures today, we'll be playing with dualities. In particular, we'll be playing with exact dualities, and string dualities are very much like other exact dualities that were introduced in Damson's lecture. We won't be talking about IR dualities in these lectures. A duality is just going to be a symmetry of the theory. It's going to be some change of variables, perhaps a very complicated change of variables, that's going to leave the observables invariant with respect to that transformation. And the reason this is often a really non-trivial and magical thing is because you these wonderful symmetry transformations are typically not manifest in any weak coupling of the description that you might have. They're exact symmetries of the theory instead. And in many of the string dualities, in fact, what we'll find is that the strongly coupled limit of one string theory, perhaps on some space-time background X, is going to be related by duality to, i.e. it's going to be equivalent to a weakly coupled string theory, in general, a different string theory on, in general, a different background space-time manifold, say X tilde. And the way I like to think of dualities morally is that they're basically Fourier transforms on steroids. And why do I say that? Well, I mean, let's recall that, let's say if I have some action for some weakly coupled theory, say a string theory or a field theory, I'll just write it like this. And for the one and only time in these lecture series, I'll have an explicit power of h bar that I'll restore before I set it to 1 hereafter. So I have my action and I've made a rescaling of the fields, which I can always do, such that the coupling constant appears as an overall factor of 1 over g squared multiplying the action. And the coupling constant, of course, only appears in this combination with h bar. So I can think about small g squared, or equivalently, I could think of small h bar. Vice versa, I could think about large g squared, or equivalently think about a large h bar limit. And a weak strong duality is going to typically transform my coupling constant to some other one that's related to the inverse. You've probably seen examples of this before. So if I tune G from a weak coupling limit to a strong coupling limit, I can trade the original description of the theory for that of the dual theory, which is becoming increasingly weakly coupled as my original theory, my original description is becoming increasingly strongly coupled. But if I want to think about things in the h-bar language instead of the language of G, the coupling, then what I'm doing when I'm doing my duality is trading a description in which quantum fluctuations are becoming increasingly large for one in which quantum fluctuations are becoming increasingly suppressed. And so this is kind of like a Fourier transform, where something that's extremely well localized in position space is very spread out in momentum space, and vice versa. Now, in a strong weak duality, in a field theory, in a string theory, in contrast to a Fourier transform, I'm not necessarily going to have an extremely nice and simple map between my field variables. In general, instead of having the nice concrete relationship between the position and momentum, like I have in a Fourier transform, what I'm going to have is some highly nonlinear transformation on some kind of infinite dimensional field space. So, it's a bit more serious than a Fourier transform. And in general, in fact, we don't always know how to map good field variables in the weakly coupled side to their counterparts, what would be the good field variables on the strongly coupled side. Although, as we'll see in cases with supersymmetry, sometimes we can, at least for some observables. Right, so, and I also should mention that, sometimes in the presence of supersymmetry, some of these dualities really do kind of turn into mathematical generalizations of Fourier transforms on the nose. And I won't have time to talk about them in this lecture, but I will talk about T-duality. In fact, I'll hopefully get to it at the end of the lecture today. And you've seen a little bit of T-duality in other lectures. I know it's come up in Sen's lectures, and we'll see it on the world sheet in this lecture. But T-duality doesn't just have an action on variables in the string world sheet, it also has an action on D-branes. I won't say much about D-branes in this lecture, I'll actually really be focusing on the world sheet. But there's an incarnation, an action of T-duality when you include D-branes in the theory. And mathematicians call this homological mirror symmetry more properly. And that really, the way to describe that duality mathematically is with respect to a mathematical transformation called a Fourier-Mukai transform, which is really, mathematically speaking, a Fourier transform or a geometric generalization of it. So sometimes in the presence of supersymmetry and with a little mathematical know-how, these dualities literally become Fourier transforms or slight mathematical fancifications of them. And more broadly, we'll see that supersymmetry is going to take us from extremely complicated, very rich physical dualities, but it's going to help us instead deal with relations between mathematically concrete, well-defined objects. And it'll help us compute observables, for example, localizing infinite dimensional path integrals to ordinary integrals, or similar statements like that. So that is where we really are going to go, mostly in lecture 3 and 4. But like I said, today we're just going to be super basic. Everyone can fall asleep if they want, if they've already seen some basic string theory. This lecture is not for you. Nothing is going to be particularly new. And I hope that's okay, because everyone is probably quite tired. But what we'll do today is introduce the classical closed bosonic string, introduce some basic technology, say a little bit about the worldsheet, and build up to our first string duality, which is T-duality, at least in its simplest incarnation, as it acts on the closed string. Okay. And oh, I should say that the plan is I will upload these kind of handwritten lecture notes afterwards, but I also have a typed set of lecture notes. I haven't decided yet if I'll upload them piecemeal or just upload them in one big document at the end, where I will have many more details and derivations that I'll be suppressing in the interest of time in these lectures. I'll have a lot of references where you can go and find alternative derivations or other explanations, and all kinds of other sources. And it'll also have various remarks connecting to more modern references as well, which, you know, in lieu of time, I really won't be able to give in real time. Okay. Classical closed bosonic string. Okay, so now we start where all string theory stories begin, with the closed oriented bosonic string. And okay, you all know what to do. You know the story. We're going to start with the theory of a classical string, and it's going to be sweeping out some two-dimensional surface in space-time called the worldsheet. So I have not pre-prepared any equations, any drawings, anything. So you get to enjoy my absolutely horrific Blackboard-style drawings in real time. And I should warn you that even in the typeset of notes, I have pictures of just I'll tech them eventually, but you know, don't expect nice figures in these lectures. You would come to the wrong place. So we'll parameterize the worldsheet coordinates by the spatial coordinate sigma along the string and the time coordinate t. So there's a closed string, and of course, an open string would look like this. Although mostly we'll be focusing on the closed string for the purposes of this lecture. So for a closed string, the worldsheet sigma is not going to have a boundary, and the open string, of course, does. And classically, we can parameterize the configuration of a string propagating in background spacetime, which for now we'll just take to be ordinary d-dimensional Minkowski space. And so we're going to parameterize the configuration of the string in our background Minkowski space by some real valued functions x of t and sigma, where m is an index spanning our d dimensions. And these are, I'll call them embedding scalars because they give an embedding of sigma into our target space, m of d. And as I think you all probably already know, if you want to try and write down a classical action for this kind of system, the first and most natural proposal that you would go to is given by a functional, well, you want to write down some appropriate functional embeddings to describe your classical string. And you can do this by analogy with the case of the point particle, which travels along a world line. And the idea is to weight any string configuration for a given worldsheet sigma by the area of the worldsheet sigma. And this is called the Nambu-Goto action, which I feel morally obligated to write down at least one time, even though we're not really going to use it. Again, as many of you probably already know. So we have an integral over sigma, and oops, I keep writing tau, but I mean to write t. so I have an integral over the world sheet with an area element that I'm labeling determinant of H. Oh, and I'm in mostly plus signature in space-time for my metric. So the coefficient in front is the string tension or energy per unit length, which is related to the string mass scale. And my 2D metric on the world sheet is induced from the ambient space-time metric by what mathematically is called a pullback. And our ambient space-time metric, well, we're just in Minkowski space, which it's the usual flat Minkowski space metric. And the formula for the pullback in terms of this eta mn, this is the flat Minkowski metric, is given in terms of the embedding scalars like this. So this is the induced world sheet metric from space-time. And as, again, you all probably have already heard, the Nambu-Goto action has this cumbersome square root in it, and it's very annoying to quantize, and we don't want to deal with it. So we will immediately forget about it. Well, very soon we'll forget about it, and we'll work with some other action called the Polyakov action, which classically is equivalent to the Nambu-Goto action. And I will sketch that in a moment, but let me write it down. So the Polyakov action works by introducing an additional 2D metric, an auxiliary metric called GAB. So we're adding an auxiliary metric. We have minus the determinant of G, GAB. It's coupling to the scalars, and we have our Minkowski metric there. And okay, why is this a good metric to write down? Well, we can just solve the equations of motion for G. I'll write it down for you just because in this lecture, I guess I'll write down some formulas. But with all of the formulas in this lecture, you're encouraged to double check them yourselves or review your favorite string theory text if you've never seen any of this stuff before, where of course everything will be broken down in much more detail than I'll have time to do today. So there's my classical equation of motion for G, and I can plug in my definition for the pullback metric, HAB. And if I do that, I'll get the following equation relating H and G. And then I can just take the determinant of this equation, get the determinant of both sides, and I can plug this result back into the Polyakov action, and you'll see pretty quickly after a line of algebra or two that I've reproduced the Nambu-Goto action again. So classically, this is equivalent, but the Polyakov action doesn't have that square root, and it'll be a little bit easier to proceed with it and quantize it. And for the remainder of the lectures, as you've probably already guessed, H bar and C have been set to 1, and 1 they shall remain henceforth. And please also yell if my writing is illegible. I think I have a little bit better handwriting on a blackboard. I'm not much of a tablet person, so hopefully the equations are comprehensible, but do let me know if anything becomes unclear when I write. So the Polyakov action has a number of local and global symmetries that we want to keep track of. So we want to preserve global symmetries, and we have some gauge symmetries that we're going to need to gauge fix if we want to proceed to quantize this classical string action. So we have a global symmetry, a global from the point of view of the world sheet, that's d-dimensional space-time Poincare invariance. Right, so from the point of view of the world sheet, it's a global symmetry. Sigma and T are not transformed, but the embedding scalars, of course, are, and they're transformed in the usual way. The usual Poincare transformations act exactly as you would expect, and the auxiliary metric B is invariant. So that's, of course, totally fine. Then in 2 dimensions, we have 2-dimensional world sheet coordinate reparameterizations or diffeomorphisms. Reparameterizations. And this is a local symmetry from the point of view of the world sheet. So if I denote my world sheet coordinates by some variable zeta, just for compactness of notation. So zeta 1 is sigma, zeta 2 is t. Then the transformations will leave the embedding scalars invariant. So I have some putative, or I have some reparameterization, zeta prime, which is a function of the original zetas. The embedding scalars are invariant, but G, the auxiliary metric, transforms as a 2-index tensor. And I'll write it down, but you all know how a 2-index tensor transforms. Again, exactly in the way you expect. So this is a local symmetry, and we're going to presently need to gauge fix it when we want to quantize this thing. And there's another local symmetry on the worldsheet, Weil invariance. And it acts as a local rescaling of the 2-dimensional auxiliary metric. So again, the scalars are invariant, but the metric transforms by some scale factor that's a function of sigma and t. So that means in total, we're going to have 3 gauge invariances that we're going to need to fix. We have the 2 parameterizations and we have the Weil scaling. But before I get to gauge fixing and quantization, let me note that the Polyakov action suggests some pretty natural and very immediate generalizations, in particular to a string propagating in some more general curved background. I mean, I chose flat d-dimensional Minkowski space, but a priori I could consider a string that's just propagating and moving along in some arbitrary background, possibly some kind of curved manifold. And let me write down that action, but it's the obvious generalization where you replace the Minkowski metric with a more general curved metric that's a function of my fields, my embedding scalars. And this is called the nonlinear sigma model. Why it's called that is some historical story that's not relevant for understanding the thing, but the supersymmetric generalizations of the nonlinear sigma model will also show up in later lectures. And I'm going to use that name a lot, so we may as well get used to it. And it's the Polyakov action, but again, I've just added some more general metric here. So previously, the Minkowski metric had played the role of the coupling constant for the kinetic term, and I've replaced it with this thing which is now field dependent. So I have my field space is now some, say, curved manifold in general with metric G, capital G, Mn. And the fact that I've done this means, in particular, that my worldsheet action is now an interacting theory, whereas the Polyakov action before was a really simple free theory. So if one were to try to study this just kind of naively, doing the most direct possible thing, well, how would you approach dealing with a metric like this? Well, what you would naturally do, of course, is to try and expand the action around a point in space-time and expand it in a derivative expansion in terms of the fluctuations of the scalar fields, delta x's, around whatever point in space-time you've picked. And it's a good exercise to just do that, write the scalars as some point, some constant point plus some fluctuations, and expand everything out. And indeed, you'll see that the interaction terms for the fluctuations come with proportional to derivatives of the metric capital G. So our loop expansion parameter from the point of view of this worldsheet field theory is the dimensionless parameter is going to be alpha prime over r squared, where r squared is going to be a typical length scale of variation characterizing the metric capital G. And I need that factor there to actually have a dimensionless expansion parameter for the worldsheet. So it's related to this space-time curvature. And so this dimensionless parameter is going to cover worldsheet loops, which are distinct from string loops, which will govern string perturbation theory. So when we talk about quantum gravitational effects, quantum effects in string theory, we're talking about the other parameter G string, which I'll introduce in a minute. This parameter, which is governing, if you like, the higher derivative terms from a space-time point of view, or these alpha prime corrections on the worldsheet, govern what's often called stringy effects. dealing with the extended nature of the string, probing my space-time. And we'll be studying dualities in both parameters. And actually, I'll focus a lot on dualities transforming alpha prime over R squared. Although, of course, dualities implicating G string are extremely interesting and indeed genuinely quantum. But studying both will be instructive for us.
Could you remind us what is R again?
R is just, for the moment, it's just some typical lengths. It's some typical length scale in my currently a priori generic background metric. So it's like a typical curvature scale for my metric. Okay. And at the end of the lecture today, hopefully I'll make it in time, we'll do basic compactification of a string on a circle, in which case R is actually going to be R, the radius of the circle. Okay. But like I said, you're choosing a point in space-time to expand around, and R is going to be kind of the typical length scale around that point in general.
Thanks.
Okay. So that's the nonlinear sigma model that kind of naturally generalizes the Polyakov action. But I also should, of course, mention at the outset that there are more general terms that we could add to our string action that obey all of the nice symmetries that I've just enumerated above. And that's, you know, at least from a kind of a effective field theory point of view, you want to try and add all possible terms you can consistent with the symmetries of the problem. And of course, the resulting terms that you can add to the Polyakov action are particularly famous. So I just want to write them down now. And of course, there's one term corresponding to an anti-symmetric tensor field, which you all know and love. And another term involving a scalar field, which you all probably already know and love. So we have the B field in the dilaton. So here, R of G is the curvature scalar of the 2D metric with respect of the 2D world sheet, excuse me, with respect to my auxiliary metric little g. Phi is some target space scalar called the dilaton, and BMN is a 2-index anti-symmetric tensor field, and that is the B field. And notice right away that the B field term has no dependence on the world sheet auxiliary metric little g. So already it's a topological term in the world sheet field theory. And in fact, what you want to do as a person of taste and culture is write it in differential form language. So you can write that term in the action equivalently up to the overall factor of 1 over 2 pi alpha prime, like this. And again, this is the sort of thing that this kind of topological term is the sort of thing that you've seen before when you are thinking about coupling a charged propagating point particle with some closed world line to a one-form gauge field. You know, this is so CF, a term like this, where A1 would be a one-form gauge field. So this is completely analogous, but for a two-dimensional anti-symmetric tensor, and it tells you right away that strings are electrically charged under this two-index tensor. And indeed, it does satisfy a gauge symmetry. And when you can verify that just using Stokes' theorem. Right, so the strings are electrically charged under the B field, and magnetically charged objects under this B field also exist in string theory, and they're called NS5 branes. And they're also very dear to my heart, but I essentially will have no time to talk about them in these lectures. But you might have naively expected them to exist just because if you have something electrically charged, maybe something magnetically charged also is a part of your theory spectrum. And indeed, that's true. So the differential form way of writing the B field makes its invariance under all of the symmetries we just talked about manifest, and it's a good exercise to convince yourself that the second term with the dilaton also does this. And if you don't want to do that, then you can open up chapter 1 of Polchinski's string theory book and you can find the argument there. But the important thing, of course, is to notice that if the dilaton is a constant, then its action in the Einstein-Hilbert, its corresponding term in my action is an Einstein-Hilbert term for the world sheet metric, little g. And we can, we also know, and I think as you've heard in your low dimensional duality lectures earlier, that two-dimensional gravity has no propagating degrees of freedom. You can gauge them all away. So if you integrate this curvature term over the worldsheet, you'll just get a topological invariant called the Euler characteristic. So integrating this term for the dilaton gives you a term like this for constant dilaton, where chi is the Euler characteristic of the worldsheet, a topological invariant that depends on the genus of the two-dimensional surface. And if we had an open string worldsheet with some boundaries, there would also be a term counting the number of boundaries. And at this point in the course of every string theory course, you know, you have to draw the pairs of pants. So indeed, the string coupling constant is related to the dilaton in this way. And one writes, constructs basic string theory interactions, and I'll draw the open string one too. And there's also one where open strings fuse to closed strings, and I'm sorry that I'm drawing these so horribly. But when we do string perturbation theory in G string, we start with these basic vertices for the string worldsheet that come with these certain powers of the string coupling constant, and we glue them together into more general Riemann surfaces on which we, you know, that govern the loop expansion of string theory. And if we're adding closed string loops diagrammatically, what we're doing is adding handles to the worldsheet, which is increasing the genus G. So making the Euler characteristic chi more negative. And in the open string, if we're adding open string loops, what we're doing is adding boundaries. Good. So that's just kind of a very quick and very schematic way to see that the vev of the dilaton is the thing that's governing the string coupling in this kind of worldsheet expansion of string loops. So for example, the genus 0 for just closed string propagation, we have, you know, the genus 0 piece. This is the lowest order in string perturbation theory. And then on to genus 1. And we just keep adding more and more holes to our string worldsheet. And so on and so on. Similarly for open strings. And of course, this fact about the dilaton is just one instance of the general principle in string theory that there are no dimensionless free parameters in string theory. All of them are fixed by vevs of massless scalar fields, which are called moduli. And the string coupling being fixed by the vev of the dilaton is kind of the first and most important example of this that we'll see, but we'll see other examples of it later on in more general string compactifications. And again, if you've never sort of studied string perturbation theory before and computed things like these vacuum to vacuum string amplitudes or more general string scattering amplitudes using all the technology of conformal field theory and stuff, highly recommend that you do read the relevant chapters of Polchinski or your favorite string theory textbook, which I know is a little old-fashioned nowadays, but I'm kind of an old-fashioned person. I have a little less than 45 minutes left.
Let's see.
Ish.
Until
7.
40 our time. Yeah.
7 my time. Yeah. Okay, great. Good. So maybe I'll also just mention that if I were focusing on open strings, which I'm largely not doing for this lecture, I could also write a natural term further generalizing the Polyakov action to account for worldsheets with boundaries. So it's an integral over the worldsheet boundary. And in view of time, I'm not going to write it in components, but it'll be in the notes, where you can also introduce a one-form gauge field on the boundaries of the worldsheet. And this turns out to modify the gauge transformations of B2, but like I'm mostly going to ignore open strings. I just want you to be aware that you can also have gauge fields coming from the open string sector of the theory, because that will come back later. And if you expand this term out in components, you'll see that it means that the ends of the open string actually couple to this U1 gauge field. And it does turn out to be a U1, well, it can be a more general gauge symmetry as you've seen when you've talked about D-branes, but in particular, the ends of the string are analogous to charged particles with charge plus and minus 1 under this gauge field. Okay, good. So that's just generalizing the Polyakov action to account for the most general terms we could add consistent with the symmetries of the problem that we have. And as I mentioned on flat Minkowski or Euclidean space, you can see from the explicit form of the action that the worldsheet theory is a free theory, even though the corresponding interactions one gets in space-time are interacting. And again, in these lectures, I won't have time to really delve into the passage from worldsheet theory to space-time effective actions, but that's an important part of understanding string theory. It's a part that I don't have time to really go into. And again, if you've never seen these things before, I do encourage you to read the relevant chapters of the textbook, of your favorite textbook. But on a more non-trivial background space-time, the worldsheet theory on its own also becomes an interacting theory in general, a strongly interacting theory. So we have these two parameters in general to play with, alpha prime over r squared and G string. Good, okay. So now I do want to move on to quantization of the string. And to be able to get to interesting things as quickly as possible, I'll use a method of quantization called light cone quantization, which is a bit of a quick and dirty way to proceed. It's not covariant. It actually completely sacrifices manifest Lorentz invariance, but it's pretty expedient and we'll be able to get to some interesting things fairly quickly. After I mostly go through light cone quantization, I will touch on a covariant method of quantization called BRST quantization without going through much of the details, partly because conceptually it's very nice, but in particular BRST quantization conceptually will dovetail very nicely with the later part of the lectures for supersymmetric theories. And I really want you to start thinking about cohomology as an extremely powerful tool for dealing with theories with gauge symmetry. And again, I expect a lot of this is largely review, but maybe you haven't seen BRST quantization or you've forgotten it from when you were quantizing Yang-Mills theory or whatever. And since the theme of this lecture series is basically cohomology, I do want to mention the BRST quantization of the closed string, albeit briefly. Okay, so let's proceed with quantizing this bad boy. So we have to gauge fix all of the symmetries that we have. We have 3 degrees of gauge freedom coming from 2 diffeomorphism invariances from our coordinates and the Weil rescaling. We have 3 gauge symmetries, gauge degrees of freedom, and we have a 2-dimensional auxiliary metric, little gab, and in 2 dimensions that has 3 independent components. So it seems that we can just fix all of those components using our 3 available degrees of freedom, because 3 equals 3. And we can just fix it to some convenient choice, for example, a flat metric. Now, it turns out that we can do this locally. Globally, there are subtleties in general on a general worldsheet sigma, and I'll postpone the global subtleties for now. But locally, this seems fine. But even with this choice, it turns out that there is a set of leftover gauge invariances that we haven't completely fixed. And those are certain combinations of diff cross Weil transformations that still preserve this flat form of the metric. So unsurprisingly, this is called flat gauge. And these reparameterizations are a set of measure 0 in the space of all possible reparameterizations, which kind of explains how it gets around my super solid counting argument of 3 being equal to 3 and feeling very powerful about my gauge fixing. Right, so let's plug in our flat gauge metric for now. I'll come back to the leftover coordinate, the leftover gauge symmetries in a minute. And well, let's plug in my flat gauge metric and just solve the equations of motion. So we're not very quantum yet. We get a pretty simple equation of motion for my embedding scalars, dt squared minus d sigma squared, and this, even I can solve it, has a very familiar solution in terms of a superposition of left and right traveling waves. So I'll be breaking up my embedding scalars into left and right moving parts that are functions of the linear combinations of the coordinates that you see there. And for expedience, I will define zeta left and zeta right to be the corresponding left and right moving coordinates. Cool. So prior to fixing the flat gauge, we had that other equation of motion for G. I wrote it somewhere. Right, we had this equation of motion for little g. And what can you do? Well, if you plug in the gauge fixed form of the metric, flat gauge, into that equation of motion, what you'll do is impose the resulting equations as constraints. I fixed the form of the metric, but we still need to impose the resulting equation as constraints on my system. And these are called Virasoro constraints. And I'll just write them in my new coordinates, zeta L and zeta R, because they look particularly simple in those coordinates. And I have my flat space metric in terms of these coordinates as well. Nothing too fancy. And now the leftover gauge invariances are pretty easy to describe. If I do some coordinate transformation that just takes zeta L to a function only of zeta L and zeta R to a function only of zeta R, then it's really easy to check that transformations like this, acting on the metric, can easily be undone by a suitable while scaling. So there's a diff cross while that leaves the metric completely invariant, and the relevant coordinate reparameter, the diff part of that, is given by these fairly simple transformations. And these probably will look more familiar to you in Euclidean signature. If I want to rotate my world sheet and take zeta L and zeta R correspondingly to be complex coordinates that I call z and z bar, then what I get are holomorphic and anti-holomorphic reparameterizations of my world sheet coordinate z and z bar, which I regard as independent coordinates, and these are conformal transformations. So I have some leftover conformal transformations, and since these diffeomorphisms only act on one variable, zeta L or zeta R as z or z bar, again, that's emphasizing that they're kind of a space of, they're not generic in the space of reparameterizations, they're quite special. Indeed, they're a set of measure zero, and that's how they got around our counting argument earlier. And again, as you guys have probably seen, I know many of you are probably conformal field theory experts, or at least have seen it in these lectures, but a two-dimensional surface, two-dimensional surfaces that are related to one another by these kinds of transformations are said to have the same complex structure. So the space of two-dimensional surfaces up to complex structure preserving transformations are called Riemann surfaces. And this is why when you compute string amplitudes, you start to see integrals over these so-called moduli space of Riemann surfaces. So that's where that nomenclature is coming into play. Good. So now let's continue on and actually do some quantization. So we have these gauge symmetries hanging around. We'll need to remember that momentarily. But now let me introduce light cone coordinates. So I'm going to privilege 2 out of the D coordinates to define these light cone coordinates. So I'm throwing Lorentz invariance out the window. X plus and minus can also decompose into left and right moving counterparts, as I will often do. And we'll write the remaining scalar fields with upper index little I, spanning 2 to D minus 1. And so now we can use our leftover conformal symmetries to make some convenient choices here. And a typical convenient choice that's often made is to choose FL and FR in a particular form, in fact, proportional to, say, the X plus coordinate, to set both the left and right moving coordinates of the X plus coordinate to be equal to T. So we're identifying one of these light cone coordinates with a world sheet time. And again, it's kind of a funky looking non-covariant thing to do, but it turns out to be a convenient thing to do, and we have enough leftover gauge symmetry to do it. And in the meantime, we've completely seemed to have thrown away Lorentz invariance. And so we're going to have to ask under what conditions after our quantization process could Lorentz invariance actually be restored, even though we've done this completely funky gauge fixing choice. Okay, so we've used all of our leftover gauge symmetry to completely fix one of our light cone coordinates, and we still have a Virasoro constraint for the other light cone coordinate, which after this gauge fixing is a pretty simple equation. Similarly for its right moving part. So there's also a right moving Virasoro constraint. And now with this gauge fixing, the Virasoro constraints are linear in x minus. So you can solve them. You can solve for x minus in terms of the other scalars xi's. And that's another simple computation that I encourage you to do at home. And that will solve for x minus with only one undetermined constant of integration. So there is one constant of integration left over from solving the Virasoro constraint, and I'm going to call it little x minus. It's a function of t. If you like, I can write it like this, where I'm parameterizing my closed string as a string of length L. So hopefully you see that this is a curly L, and I'm integrating over sigma. So we still have a little degree of freedom there from doing this. And we can take all of that and we can plug it in. We can write down the Lagrangian. Yeah, what the heck, I'll write it out. Again, if you've never done this, these are all just some simple classical manipulations. You should definitely check them on your own. It's a fun little exercise. So we plug things in, we get a Lagrangian. Nothing very exotic. And you can then take your degrees of freedom, little x minus and the capital Xi's, and you can also compute their canonical momenta. So the canonical momentum of x minus is p minus, which is equal to minus p plus with an upper index because the light cone metric, has components like this. I won't give all the details, but this is all probably quite familiar. So the string length and light cone gauge is growing with momentum in the positive light cone direction. And you can also, of course, compute the conjugate momenta for the capital Xi's. You all know how to compute conjugate momenta. There it is. And in terms of the conjugate momenta, we can take our Lagrangian and we can write down the Hamiltonian. And what the heck, since I'm writing down a bunch of formulas today, I assure you there will be substantially fewer formulas in subsequent lectures. But you might as well get the Hamiltonian while you're at it. Lo and behold, it is a Hamiltonian of d-2 free massless bosons in 2 dimensions. Can't get much simpler than that. It's the great thing about doing worldsheet string theory in Minkowski space. Everything's about as simple as you could want. Okay, so let's proceed from here and start preparing for canonical quantization, as we all love to do so much. And it's convenient to take our remaining scalar fields, the capital Xi's, and split them up into their left and right moving parts, and write them in a mode expansion. And since we're dealing with closed strings primarily in this lecture, we have to impose the condition that our mode expansion is consistent with the periodicity of the closed string. So if we shift the spatial coordinate by the string length L, the mode expansion should come back to itself. And so the mode expansion then is not hard to write down. Again, you've all probably done similar things already in your courses, if not this exact thing. There's some conventions involving normalizations. I've just chosen a particular one. The precise factors that appear in this formula are not important. But we have our familiar and beloved mode expansions for the scalar fields. And it includes the first 2 terms, which are are the center of mass kind of position and momentum terms, which are equal to one another by this periodicity constraint on the closed string. And we also have an infinite tower of oscillator modes. One set for the left movers and one set for the right movers. And so far, they're completely independent. The periodicity of the string ties these variables together, ties the momenta together, but the oscillators are just two independent sets of decoupled oscillator modes. Right. Okay, so now we just canonically quantize. So we have our degrees of freedom. We've computed their canonical momenta, and we can impose canonical commutation relations on the position and momenta as we always do. And that will translate in terms of these mode expansion variables to the following commutators. So the center of mass degrees of freedom are completely standard. The left and right moving oscillators commute with each other, but have non-trivial commutation relations among themselves. And indeed, after you rescale these oscillators, you see that this is nothing but the same commutation relations you've seen for creation and annihilation operators in a harmonic oscillator. Good. So in terms of these modes, we can rewrite the Hamiltonian after canonical quantization. And as always, when we do this, there's an ambiguity of ordering, of how we order the modes. And this is the part where I'm going to be a little bit telegraphic with the details, partly because they're treated very carefully and much better in standard text, partly because it's boring and you guys are all exhausted. But we'll take the standard normal ordering convention where we move our negatively moded operators all to the left and the positively moded ones to the right, which will correspond respectively to the creation and annihilation operators. Of our system. And once we do this, there's also some 0-point energy in the quantum mechanical system that we have to account for and compute. And you can compute this thing in a variety of ways, some of which cheat a little bit more, some of which do things really properly. The kind of quickest way is to zeta regularize an infinite sum over the 0-point energies. I'm going to completely skip all of the ways of doing these computations and just tell you the answer. That all of the ways of doing the computation agree, and they give you a constant answer for these 0-point energies in terms of the space-time dimension of our target space. And in fact, having a divergent sum at all is, well, there's nice ways to get around having to do a divergent sum that involves tracking the symmetries of the problem a little bit more carefully. And again, Polchinski does this totally in the most beautiful way. Great. So we have a quantum mechanical system with a Hamiltonian. It includes two decoupled sets of an infinite number of harmonic oscillators. And we also have just the simple quantum mechanics of the center of mass modes. So as always, we just want to define a ground state to be annihilated by the sets of our creation operators, which correspond to positively moded operators. By these commutators. And then we want to build the Hilbert space by acting on the ground state with creation operators, which in these cases are the negatively moded operators in all possible ways. And the ground state also is an eigenstate of the center of mass momentum operator pi with some eigenvalue. So sometimes in the notation, I might make that explicit, just that it's a state of definite momentum. Or I might label it by 0 if I'm getting super lazy. But in particular, we're defining the ground state around which to build our Hilbert space, as always, by the condition that it's annihilated by the positively moded things, and then we build it up from there. Let me also, before I do that, mention one thing briefly and introduce a little bit of notation, which is that it's convenient to write, to define these oscillator numbers again, which you've probably already seen in the context of the harmonic oscillator. So this is the oscillator number, similarly for the right movers and tilde. And we, so far the left and the right movers have been completely decoupled from one another, but they're not completely decoupled from one another. And in fact, there's various ways of phrasing an extra constraint that we have to put on these guys. There's various ways of phrasing this condition. It's called the level matching condition. One way of stating this condition is that we haven't sort of taken care of the fact that, we haven't imposed the fact that our theory should be independent of translations around the spatial coordinate. Like I have expressions where I'm integrating sigma from 0 to L, it's a length L string, but I've made some arbitrary choice of where sigma equals 0 should be as some reference line. Physics has to be completely independent of any parameterization of the string itself. So one way of phrasing this condition, if you like, is to impose that translations along the sigma direction had better be trivial. Like I said, depending on the treatment that you find in the text, there's other ways to phrase this, but in particular, one can compute that it's proportional to n minus n tilde. So in particular, the oscillator numbers of the left and right movers have to be equal to one another, n equals n tilde. So this is called the level matching condition, and it's basically from the point of view of the closed string, it's the only thing that's keeping the left and right movers talking to each other. Otherwise, they're completely decoupled. We can compute things with them essentially independently, but we have to remember that this constraint has to be satisfied. And of course, so different string oscillation modes that we're going to build up shortly in our Hilbert space will correspond to some particles in space-time of various masses. And we know m squared equals minus p squared, which in light cone coordinates we can expand out. So this is the usual mass shell condition in space-time. And if we want, well, one of these momenta by our gauge fixing, we can identify by time translations. Therefore, it's equal to the Hamiltonian. I can plug the Hamiltonian in. I can simplify things. Again, this is kind of a fun and super simple thing to check. But the mass shell, the formula for the masses of the particles coming from the oscillator modes of the string looks like this. And now, okay, now we can actually start talking about the masses of, say, the lightest few particles in my closed string spectrum. So we're going to act with oscillators on the vacuum, subject to this level matching condition. Nothing could be simpler. Of course, we can start with just the vacuum state, n or equals n tilde equals 0, which tells us that the mass, if we plug in the formula for the 0-point energies, is just this. So that corresponds to just this bare state. And the next one, which I'll also write down, has the oscillator numbers both 1, and I can plug in the mass for those two. And it's, if I get the factors right, it's this. And that corresponds to just acting. This is I, this is J on the vacuum state. Okay, so let's think about these states in particular. So manifestly, these states are a 2-index tensor of SOD minus 2, because in our light cone gauge, we have fixed 2 coordinates non-Lorentz covariantly. So it's transforming into some representation of SOD minus 2. So if these were some massive particles in our space-time, we would say, okay, we want Lorentz invariance in our quantum theory to be restored, even if our gauge condition seems to be breaking it. And indeed, we demand that of our theory, at least for the purposes of this lecture, right? So what do we really want? Well, if these were massive particles in our d-dimensional space-time and Lorentz invariance were really there, we would hope that somehow the states would reorganize themselves into representations of the little group for, say, massive particles in d dimensions, which would be SOD minus 1. And try as you might, you cannot make this 2-index tensor of SOD minus 2 reorganize itself into a representation of SOD minus 1. I dare you to try it. You can't. Okay, so that seems like we're in trouble now. But I mean, there's an obvious way out because I've been saying massive particles. And you all know, of course, that if instead we were thinking about the little group of massless particles in d dimensions, then the relevant group would be SOD minus 2. And so if we want to wave our hands and be a little bit sneaky with things, let's say we demand that these states correspond to massless particles to restore the Lorentz invariance that we've broken with our ridiculous choice of gauge. And if we do that, and if we set the mass formula equals to 0, then this tells us that the space-time dimension is 26, which is a quick and dirty way to derive the so-called critical dimension for bosonic string theory. And in the superstring, which I'll introduce next time, but I won't go through all of these details again because they are very, very similar, the analogous computation for the superstrings give d equals 10, the famous critical dimension of the strings. And if you work harder and you build up more and more massive states in the Hilbert space, you indeed see that with this choice of d and only this choice, do the states in fact reorganize themselves properly into representations of SOD minus 1, the massive little group. There's other ways to get to the critical dimension, which are more elegant. I'm just kind of giving you a quick way to see it. And that means that this state here has negative mass squared. It is the tachyon. You know, we have the presence of a negative mass squared particle indicates that we're expanding around some extremum of a space-time potential that's not really a local minimum. We don't know the fate of the bosonic string tachyon, but you know, it means we don't really want to work with bosonic string theory, but it's an illustrative kind of test case to learn a little bit about string theory before you introduce all the complications of superstring theory. Okay. Well, so there's the tachyon. It's going to get projected out in the superstring, as you all already know. But when it comes to these massless states, we have a 2-index tensor of SOD minus 2. So that's SO24. And a 2-index tensor can be split into a symmetric traceless tensor, an anti-symmetric tensor, and a trace piece. And that's nothing but the metric, the B field, and the dilaton that we have seen before. So that's reassuring. Okay. So I want to compactify the string on a circle and tell you about T-duality before I run out of time. But before I do that, I just want to remind you that BRST quantization exists. And I want to remind you of it because it's important for modern mathematical physics, because it's an elegant way to quantize the string, and because it's going to really dovetail nicely with a subject called topological twisting of supersymmetric theories that we'll meet again in lecture 3. So I want you to have this kind of thing in mind, and maybe some of you already know about it. Again, the basic idea here is a covariant way to quantize your favorite gauge theory, including our 2D world sheet string theory, using the mathematical techniques from cohomology. So actually, I don't know if I have too much time, but can you guys give me like the yes or no vote on if y'all have seen BRST before? Do you need a reminder or not? So like, yes, if you are comfortable with BRST methods, Faddeev, Popov, ghosts, all of that. No, if you'd like me to just briefly say some words about how this is going to work in the bosonic string. And I will attempt to scroll. Okay, a couple no's, couple yeses, some no's, some yeses. Okay.
And you have 10 minutes.
And I have 10 minutes. Okay, so you know what? Let me defer BRST for next time because it's a bit logically independent. So I'll make a note to do that at the start. And let me go right to compactifying the closed bosonic string on the circle so that I can introduce T-duality, because I feel that I should give you at least one string duality today. You know, otherwise, what's the point of the title of this lecture series, right? Okay. So we'll do BRST really quickly next time. Good. So we have, next time. Okay, so we thought about the bosonic string in Minkowski space. or Euclidean space if you want to change signature. And now we can start thinking about string compactification on more general manifolds of the form, say, some dimensionality of Minkowski space times a compact manifold in the remaining dimensions X. And we know what the simplest kinds of compact manifolds are. They would be 26 minus d dimensional tori, where the simplest tori is going to be an orthogonal product of d circles. And the simplest torus is a circle itself. So let's compactify on a single circle of radius capital R. It still has a flat metric, so everything is basically as simple as could be. The only non-trivial thing is that, okay, locally everything is still flat, so most of our analysis will go through, but globally you can view the circle as a quotient of the real line by some shift symmetry, and so there's going to be an extra kind of global subtlety that leads to some interesting physics. So first, if we want to not think about strings just yet, we can start by thinking about the result of doing a KK compactification on a torus. And as we've discussed, well, the effective field theory that would be capturing the massless string modes resulting from this kind of setup would be a good description if our effective string parameter is really, really small. That's basically approaching a point particle limit where the extended nature of the string is suppressed, the higher derivative corrections are suppressed, and here R is really now just the radius of the circle. That's our dimensionless parameter. So in 26 dimensions, the massless field content was the metric, the B field, and the dilaton. And if you want to just do a field theoretic KK reduction, where keep in mind this is only a good approximation to our string theory in this parameter regime, then, well, again, probably most of you know what to do, but this is the review lecture, so we're taking it easy today. You treat, say, one of our space-time coordinates, say the 25th one, as periodic with this identification, and you can expand the x25 dependence for all of our fields, phi, well, let me not use the same phi for the dilaton, some generic field phi, we can always expand it in Fourier modes. If we're just doing a KK compactification, you expand the field in Fourier modes and you plug it back into the action. You write everything out. And you find that you get a tower of states, an infinite tower of states with masses that go like k squared, the momentum mode over r squared. And if we were compactifying some massive fields, we would shift it by the bare mass parameter, but the metric, the B field, and the dilaton are all massless. And if we're studying the theory at energies much lower than 1 over r, then the resonances coming from the KK modes are, they're very massive. And so we can just look at the massless field content. And we'll also assume that the string resonances are much less, the string resonances are much heavier than the KK resonances. So the things coming from acting on our vacuum with the higher moded alphas and alpha tildes. Okay, so the massless field content you can do pretty straightforwardly. So in the view of time, I'm just going to be brief. Of course, if you compactify the metric, then you have components like this. So you still get a metric in 25 dimensions, but you also get a gauge field, which has a U1 symmetry. That U1 symmetry is nothing but the diffeomorphisms along the circle, the U1 translations along the compactified circle. And the corresponding charge modes are the KK modes, the modes where momentum is the corresponding charge for the U1 gauge symmetry. And you also have a scalar field. And this scalar field is called sigma, and it turns out that it has no potential in the compactified theory, so it's a massless moduli, and in fact, its VEV sets the radius of the circle, which works with the earlier lesson that we had before. Compactifying the dilaton just gives you back the dilaton, and KK reducing the B field, again, gives you a B field in 25 dimensions, but you also get another gauge field, as it turns out, a U1 gauge field A hat. And from the point of view of the massless effective field theory, there's actually no states charged under this A hat, but the corresponding charges do exist in the string theory, and they're called winding charges. And we'll get to that now. And I think I can do it in the remaining 5 minutes. So let's actually think about the more general string states. The massless KK compactification, okay, that's That's nice, but it's not the full story. So we're thinking about our string on the circle. And for most of the xi's, in dimensions 2 through 24, everything we did is exactly the same. But in the periodic 25th dimension, we want to allow for a more generalized periodicity condition. This is the only novelty of circle compactifications. We can allow that it comes back to itself up to this additional term, where W is an integer, and it's called the winding number, and it's keeping track literally of how many times the string is winding around the circle when you take sigma to sigma plus L. So the field theoretic KK analysis that we just did comes from the W equals 0 sector of the theory, but there are all of these other sectors for any integer value of W. And the mode expansion of X25 alone is different from what we previously saw. So the oscillator stuff is all the same, so I won't write it down, but the center of mass degrees of freedom are more interesting. It basically comes from the del sigma of X25 term in the action. But you notice here that first of all, the center of mass momentum is quantized, as happens when we put the theory on a circle. And we also have this additional contribution that depends on the new winding number. The Hamiltonian is basically identical to the flat space case, except we get an extra contribution from the winding sectors. So there's another term that depends on R times W that I won't write down. And if you recompute the level matching condition, you now find that it's modified to a condition like this, that the difference in the oscillators has to match the momentum times the winding. And similarly, we can go through all the same steps and recompute the mass shell condition with this modified X25, and we get the following thing, where now I'm actually plugging in the correct value for the 0-point energies to get this -2 here. But when W equals 0, you see that I have a tower of KK modes, as you would expect. And additionally, we have all these stringy modes coming from this R squared W squared over alpha prime term. And I won't prove it, but if you plug it, if you study the effective action, you do find that this A hat field does couple with charge little W. So sorry that I have to be a little bit quick and skip that. And just as in flat space, we can split the mode expansion for X25 into the left and right moving modes. And you have to write down these expressions. This is classic stuff. Even when you're running out of time, you have to do it. The left and right moving center of mass modes, when you split up X25, take the following form. Okay, so 1 minute, I can tell you what T-duality is. This mass shell condition is invariant if I replace R with R prime, which is alpha prime over R, provided I also swap the momentum and winding modes of the circle. So the spectrum of particles is identical if we compactify on a circle of radius R, or if we compactify on a circle of radius alpha prime over R, provided we also exchange the momentum and winding quantum numbers. So when one duality frame is described well by classical geometry, the other duality frame is necessarily highly stringy, and vice versa. So remember, the string parameter is this alpha prime over R squared. So for example, if we shrink our one circle, R goes to 0, then notice from the mass shell formula that we have an infinite tower of winding modes becoming light. Whereas the corresponding picture in the dual frame, where R prime is going to infinity, by contrast has an infinite tower of momentum modes becoming light. So say in our first frame with R, all of this light infinite tower of winding modes is reorganizing itself secretly into a large dimension R prime. So that's T-duality. I want to emphasize that it is a strong weak duality only in the stringy parameter alpha prime. It is not a strong weak duality with respect to the dilaton. If we study 25-dimensional effective actions and set the corresponding 25-dimensional Planck scales equal to each other, what you'll find is a relationship between them like this. So indeed, not a strong weak duality in the stringy frame. And I want to emphasize that even though I phrased it as a symmetry of my mass shell formula, it's more than that. It is an exact symmetry of the string theory because you can show it actually just comes from a symmetry on the world sheet that takes PR, the right moving momentum, to minus itself while fixing PL, which, if you like, comes from alternately considering the left and right moving splitting of X with a minus sign instead. So there's just an extra minus sign that implements this transformation, and all of the worldsheet OPEs are invariant under this transformation because the minus sign will cancel in pairs. So it is a symmetry of the full worldsheet theory. And at the level of the stuff that we've written down, it's worldsheet parity on the right movers. So I am out of time. But again, just to emphasize, this is our first string duality. It's really a symmetry of the full string theory, and it's a completely trivial, innocuous symmetry of the worldsheet theory that has a dramatic consequence in space-time. We have changed the space-time geometry quite radically by fiddling with some minus signs on the worldsheet. And we'll see this kind of thing again in more interesting dualities where supersymmetry is involved. And well, I'm out of time, so thanks.
Perfect timing. Thanks very much. All right. So questions for Natalie.
Yeah, I'm hoping this was mostly review so you guys could kind of just rest and feel happy that you already know all of this stuff, or kind of refreshing your memory. But if not, please don't be shy.
No recorded questions? Should we then go to unrecorded questions?